So far in our discussion of decision theory, our focus has been on making decisions when we can easily assign numeric values to the choices. Things like amounts of money or quantities of time or amounts of stuff produced. But what if I'm trying to decide something like whether to make chili or pasta for dinner? How can I quantify any difference in value that I might place on these two choices? We'll be able to do that with the concept of utility. That will allow us to quantify the difference. So in this lesson, we'll define what utility is and look at how to calculate expected utility. We'll explain the relation between utility and preferences. We'll show how to use a specific decision problem to determine a value for our utility. And we'll end by illustrating the diminishing marginal utility of money. Previously, we showed that buying lottery tickets has a negative expected monetary value. So the example we looked at was one where our tickets are $2 each, the lottery paid out 30 million, and the lottery was going to sell 20 million tickets. We calculated that for this lottery, the expected monetary value of a lottery ticket was losing 50 cents. So we're left with this question. If people expect to lose money when they buy lottery tickets, why would it make sense to do this? It still seems like it could be rational to buy a cheap lottery ticket now and then, doesn't it? What could explain that? The issue is that expected monetary value doesn't capture everything we put value on. So we need a way to measure sources of value that are not just money. We may value, in this case, something about the fun of the risk of a gamble, or the fun of imagining what we would do with our lottery winnings if we were to win in that small chance. On the other hand, it may be less worth it if we need the $2 to get a bus ticket home. The concept of utility will give us a way to give a numeric value to these additional things we value, like risk, or the fun of imagination, or the loss of the ability to purchase a bus ticket. So utility is an abstract way to measure or assign numeric value to the total value a decision maker places on an outcome. By using utility, we can weigh an agent's preferences for alternatives that can't be measured or can't only be measured in terms of money. So let's consider another example. Let's think about the value of a pizza. Imagine that you're willing to pay $18 for a really good large pizza, and you're also willing to drive 10 minutes down the road to pick it up. That tells you that the value of the pizza is more than just the $18 you're willing to spend on it. It's also worth a little bit of time, the cost of the bit of gas you use, and a little bit of wear it puts on your car. In this case, your utility for the pizza should be more than your utility or the value you place in the $18. We'll call the numeric quantities we assign for utility sometimes utils, as in getting a delicious large pizza has a value of 0.75 utils for me. On its own, this number is somewhat meaningless, but we'll see in a minute that it makes sense not so much to assign utilities to everything we might want or want to avoid, or to assign numbers haphazardly, but rather to assign utilities for a particular decision problem, like should you order pizza or a burrito. And what matters most when we assign these numbers is that we show what outcomes we prefer more than others, as well as how much more we prefer them. The relative utility values we assign to outcomes should reflect our relative preferences. Now, these utility values are subjective. Utilities are subjective. That means that the utilities you assign to outcomes will reflect your unique preferences. That's because your preferences are what should guide the decisions that are best for you. So if I prefer some outcome more than you do, that outcome has a higher utility for me than it does for you. Let's say I prefer cooking with jalapenos over cooking with bell peppers. Then cooking with jalapenos should have a higher utility for me than cooking with bell peppers. And if you don't like jalapenos, then your utility for cooking with jalapenos should be lower than my utility for cooking with jalapenos. For shorthand, we'll use a couple of symbols to represent our preferences for different outcomes. So if an agent prefers some outcome A to some outcome B, we'll write A and then this sort of curvy greater than symbol B. And if an agent is indifferent between two outcomes, A and B, we write A tilde B. That basically means that to this agent, A and B are two outcomes that are equally good. They would be equally happy or unhappy with both. So for example, if J stands for the outcome where I cook with jalapenos and B stands for the outcome where I cook with bell peppers, then J curvy greater than B means I prefer cooking with jalapenos to cooking with bell peppers. We'll just read this symbol as prefers. Then when we know someone's preferences, that will put a constraint on the utilities we assign to their outcomes. So take two outcomes for some agent A, and those outcomes we'll call A and B. We have to make sure we assign the utilities as follows. If the agent prefers A to B, then the utility of A has to be greater than the utility of B. And if the agent is indifferent between the outcomes A and B, then the utility of A has to be equal to the utility of B. These rules can always serve as a check on whether or not the utilities you assign make sense. Now, why have we focused on utility? Remember that our goal is to switch from calculating expected value to now calculating expected utility. We want to be able to calculate the expected utility of various choices in a decision problem because expected utility will take in all of the different considerations and preferences that should impact a decision that we make. So instead of calculating the expected value or expected monetary value of a choice, we'll calculate its expected utility. You'll see that the formula is exactly the same as for expected value, but we'll be calculating the payoff of each outcome in utils instead of dollars or hours or whatever we were looking at before. So the formula is as follows. Take some choice A. If you make choice A, there are n possible outcomes, where n is some number, 3, 4, 70. We'll give the outcomes in the list as C1 to Cn, C for consequence, just because outcome O looks too much like 0. The expected utility of choosing A, given that A can result in consequences C1 to Cn, is given by multiplying the probability of consequence 1 times its utility, and the same thing, probability of consequence 2 times the utility of consequence 2, all the way up, probability times utility for each consequence for however many there are. So again, if you compare this formula to the formula for expected value, you'll see that the only change is that we're talking about the utility of outcomes associated with a choice instead of the expected value of those outcomes. And again, the benefit of this calculation, this formula, instead of what we've looked at before, is that utility allows us to take into account all the preferences that might impact our decision. And then the guideline for a rational decision is similar to what it was before. Our goal is to make the choice that maximizes expected utility. And that's because doing so gives you the best chance of getting a more favorable outcome. So let's look at our lottery example again and show that when we assign utilities to the outcomes, we can show that it can in fact be rational for someone to buy a lottery ticket, even if they expect to lose money every time they buy a ticket. So just to repeat the stakes, you're thinking about buying a lottery ticket. Tickets were $2 each. The lottery pays out $30 million if you win, but the lottery plans to sell 20 million tickets. And a reminder that when we calculated the expected value before, we got negative 50 cents. So a 50-cent loss. Now let's consider the utility of buying a ticket instead. The following decision matrix gives the utilities of each outcome, as well as the probabilities of each outcome. The probabilities are given to you in this problem already, because you know that there are 20 million tickets, so you have a 1 out of 20 million chance. So the probabilities are the numbers in parentheses. And then here I'm going to give you a reasonable number for the utility of each outcome. We're going to use a scale where utility, like probability, must be between 0 and 1, where 0 is your worst outcome relative to this decision, and 1 is your best outcome relative to this decision. So buying a lottery ticket and winning might be something you would want more than anything else in these circumstances, though maybe there are a few minor downsides, so it's not absolutely the best thing in actuality. So we'll give it 0.99 utility. Buying a lottery ticket and not winning means you lose your $2, but you get to have a little fun with the risk of gambling and imagining what you might do with the money. So the utility of a non-winning lottery ticket is a little bit closer to your best outcome, but it's still pretty close to your worst outcome. But it has some upside. If you don't buy a ticket, you can't win. So we can't assign a utility value there above 0. There's no change. And if you don't buy a lottery ticket, you're guaranteed not to get a winning ticket, but you don't lose or gain anything. So that gets a utility of 0. From this decision matrix that lays out these utilities and probabilities, we can calculate the expected utility of buying a lottery ticket or not buying one. We have to separately calculate the expected utility for each of these two possible choices on the left. So in each case, we add up the products of the utility of the outcome and the probability of the outcome. And we can get those values from our decision matrix, since that's got the probabilities and utilities of each outcome. Since each row captures the outcomes associated with a different choice, we can read across each row to get the values relevant to the expected utility of buying a ticket and then the expected utility of not buying a ticket. So if you look at the formula for buying a ticket, for don't buy a ticket, in both cases we multiply the probability of winning in that row times the utility of winning plus the probability of losing times the utility of losing. So the probability of winning if we buy a ticket is 1 in 20 million, and the utility was 0.99. And the probability of losing is almost 1. But the utility of losing is positive. It's 0.1. We get a little bit of utility. Running the numbers, because the chance of actually winning is so low, that's essentially 0 utility, expected utility. But the chance of getting a little fun is basically guaranteed. So we end up with an approximate expected utility of 0.1. On the other hand, what's the expected utility of not buying a ticket? It's basically that there's no change. We don't have any additional fun, but we don't lose out on anything either. That has an expected utility of 0. So the utility of buying a ticket is a little higher than the utility of not buying a ticket. That tells us it's rational to make that choice. You should expect a little benefit from buying the ticket, even if you don't win. Now, we already explained that utility is a measure of our preferences. But now there's a further question. How do we turn preferences into utility numbers of the kind that we assigned in the previous decision matrix? Those ones were given to us. But what if we wanted to figure out our own? Well, we can't really look into people's heads and see what they prefer or read off numbers from those preferences. But we can use people's choices to reveal their preferences. We already saw that if an agent prefers outcome A to outcome B, the utility of A will have to be higher than the utility of B. And in general, we assume that if someone chooses A instead of B, jalapenos instead of bell peppers, they prefer A to B. Well, it turns out we can get a precise measure, or at least a reasonably precise number that meets our conditions, if we measure the utility of an outcome in terms of the risks you're willing to take to get that outcome. So we're going to use a gamble to calculate the utility of an outcome. So take some outcome, we'll call it C. We want to calculate the utility of C. And we're going to use the following gamble. Either you get the outcome in question, C, for sure, guaranteed, or you take a gamble that has a chance of getting your worst outcome and a chance of getting your best outcome. So the best and worst outcomes can be tied to a particular decision problem. So if we're choosing what to eat, the worst food might be the 10-day-old leftovers in our fridge, and maybe the best would be delivery from your favorite local restaurant. We can also treat the best and worst possible outcomes overall if we want to give an overall utility ranking. And in that case, the best and worst outcomes would be whatever our personal version of heaven and hell is. Or at least that's a useful way to think about it. When we use a utility scale from 0 to 1, like we did with the lottery case, the benefit will be that it gives us a direct way to assign numeric utility to our preferences. So we're going to call our best outcome B, and the utility of B will be 1. So that's the maximum. The utility of our worst outcome, W, the one we want to avoid over all others, will be 0. Those are the two ends of the scale. C, presumably, is going to fall somewhere in between there. And we want to figure out where. So again, the gamble is either you get C for certain, or you gamble between the best and worst possible outcomes. With this gamble, we have to figure out the probabilities of the best and worst outcome. So it'll be kind of like gambling on a coin flip, only this time we get to assign these hypothetical probabilities. And our goal will be to assign the probability of our best outcome that makes us indifferent between choosing A and B. Where A is you get the consequence in question, C, for certain, and B is the gamble, where you have a chance probability of B of B being the case, your best outcome coming true, and a chance of 1 minus the probability of B, of W being the outcome. So you're sliding between this 0 and 1 scale of probability and figuring out what number between 0 and 1 as a chance of your best outcome would make you indifferent between gambling for your best outcome and getting C for certain. Remember, our goal in this funny puzzle, this funny choice, is to determine your utility for C. And what it turns out to be is that when you're indifferent between outcome A and B in this choice, your utility for C can be given by whatever probability of B makes you indifferent between these choices. So how did we get that the utility of outcome C is the probability of our best outcome? That comes from how we set up the gamble and the scale of best to worst options. So remember, the scale from worst to best was 0 to 1, and that was just like our probability scale. So that already tells you that there's going to be some numeric correspondence between utility and probability. Then we're going to end up using our expected utility formula and the fact that we're indifferent between these two choices to show that the utility of C is the same number as the probability of B. So here's how the calculation goes. We're setting things up so that we're indifferent between these choices A and B, C for certain, and the gamble. Since we're indifferent, we know that the expected utility of choice A has to be equal to the expected utility of choice B. Now, the expected utility of choice A is straightforward. It's going to be the utility of C, because there's only one outcome, you get C, and it's certain. So you get whatever the utility of C is times 1, that's the utility of C. So that takes care of the utility of choice A. To get the utility of choosing B, we have to calculate the expected utility of this gamble. And for that, we have to use our expected utility formula. We multiply the chance of our best outcome times its utility, and add that to the chance of our worst outcome times its utility. So that's what's shown there on the third to last line. In the second to last line, we plug in the utilities of the outcomes B and W. Since the utility of W is 0, that term's going to cancel out. Since the utility of B is 1, that just gives us the probability of B. Anything times 1 just gives you itself, right? So the utility of the outcome C just is equal to the probability of B in this particular gamble. And that's just what we said from the start. Now that gamble might be a little bit confusing, so let's look at an example where we calculate the utility of a particular outcome using the choice between getting the outcome for certain and the gamble. So we're going to try to figure out what's the utility of getting $100. That tells us how much $100 is worth to you. And let's call B, the best outcome, the one where you have as much money as Jeff Bezos. And W, that will be your worst outcome. That's where you get nothing. So our goal is to assign a probability to getting the amount of money that Jeff Bezos has, so that we're indifferent between getting $100 for certain and gambling for Jeff Bezos' money. So how likely would you have to get the Bezos billions in order to take that gamble over $100 for certain? Chances are that the probability could be pretty low. $100 is a decent amount of money, right? It could pay for a good amount of groceries, for example. But the gamble gives you a chance to get more money than you could basically ever spend. So we have to figure out some probability that makes you indifferent between just getting $100 and making the gamble for Bezos's money. I would think that for most people, the chance of getting the fortune could be pretty low for you to give up or be indifferent between gambling and getting the 100, even if $100 might make a decent difference to your month. Again, whatever your utility will be is going to be subjective. But I figured, $100, I could do a fair amount with that, right? It would really help me pay for some groceries, but I would never have to worry about groceries again if I gambled for Bezos's money, and I could afford to lose $100 or not get it. So I would probably be indifferent between the $100 and the gamble if the chance of getting Bezos's money was about 1 in a million. If you think you would be indifferent with a slightly different chance, you should write it down. Remember that this number, 1 in a million, that's the chance that you would be willing to gamble for or get $100. 1 in a million or 1 over 1 million also tells you your utility for $100. What matters, though, is not that this is a small number, but how that number compares to your utility for other amounts of money. So let's now imagine the same choice for 2 different amounts of money, and we'll compare our utility for $100 to our utility for $1,000 and our utility for $2,000. $1,000 is a more meaningful amount of money. It's the kind of thing that might cover a month of rent plus or minus some. So you might think you'd have to have a pretty decent chance at the Bezos fortune to give up $1,000 for certain. One way to think about it: how likely would you have to be to get billions of dollars out of a gamble in order to give up getting $1,000? I'm going to say it's maybe 1 in 10,000. Now, first we should note that since we prefer $1,000 to $100, our utility for $1,000 should be higher. And it is. 1 in 10,000 is higher than 1 in a million. In fact, our utility for $1,000 is 100 times as great as our utility for $100, even though it's only 10 times as much money. Now let's consider one more choice: $2,000 and the gamble for the amount that Jeff Bezos has. When the jump was $100 to $1,000, that made a pretty big difference to how high the chance would have to be for you to give up the 1,000 or being different between having the 1,000 and making the gamble. But I bet for most of you, as it does for me, the difference between 1,000 and 2,000 doesn't feel as big as the difference between 100 and 1,000, even though it's actually a bigger increase in the amount of money you could get. So I think maybe I would be willing to take either the gamble or the 2,000 if I had like a 1 in 8,000 chance of getting Jeff Bezos' money. Again, if you think you have different values for each of these, you should write your own probabilities and utilities down. So we've weighted the gambles for Bezos' billions versus getting the money for free, and these are the utilities for money we've assigned. $100 has a utility of 1 over a million, $1,000 has a utility of 1 over 1,000, and $2,000 has a utility of 1 over 8,000. Again, to go from $100 to $1,000, our utility for the money went up by a factor of 100. But in this case, to go from $1,000 to $2,000, our utility for the money didn't even double. This actually reveals something interesting about the way people usually value money. So comparing these utilities we assign when we consider these gambles shows us what's called the marginal utility of money. So marginal utility is the difference, the change in utility when you gain more of something. So again, the difference between the utility of $100 and the utility of $1,000 was an increase of 100 times for a difference of $900. And the change in utility of $1,000 to $2,000 was an increase in utility of just 1.25 times for a difference of $1,000. That tells us that if we had the chance of $1,000, the difference of an extra $1,000 wouldn't be that much. So for most people, the marginal utility of money decreases with higher amounts of money. In general, as we stand to gain more money, each additional dollar is worth less to us. Now, there's going to be some variation along the way, and how much the marginal utility of money decreases will depend on the person, of course. Note too that we have diminishing marginal utility for other things as well. So, for example, if you're still hungry, a slice of cake is delicious. It'll have a pretty high utility. But then an additional slice of cake after that might not make you that much happier. And an additional slice of cake after that might be worth than nothing, because you'll start to get sick. And with that, we have the basis of our introduction to decision theory. So you should now know how expected monetary value, and expected utility differ. You should be able to use expected monetary value, and expected utility to determine what's the rational choice in a decision problem, and also know why each of these show us a rational choice. You should be able to set up a decision matrix to represent the choices and states in a decision problem. And you should be able to calculate someone's utility for an outcome from their preferences, and in particular by using a choice between some outcome for certain and the gamble between their best and worst outcomes.